Okay, how about this then? So at this point, we don't have, our, we know some tricks, we know some derivative rules, right? But we don't know very many. Really, the only one that we know of any significant, well, we know sine and cosine also, but those are the next assignment. For this assignment, the only rule we're using is the power rule, right? Now, we know that we can, if we have a polynomial, we can just differ, or it doesn't have to be a polynomial. If we have a function that is a series of terms, we can differentiate term by term. But we cannot do something like take the derivative of the top and then the derivative of the bottom separately. That doesn't work. The quotient rule, I'm going to show you that today. That's the topic of the day is I want to show you two new rules, the product rule and the quotient rule. But even knowing those, this would be a problem that would always be easier to do without using the quotient rule. The quotient rule is a little bit hard to apply. It's sort of messy, not horrible, but we would rather, if we could, always write a function as a string of terms and then differentiate term by term. Does that make sense? I think this would be a pretty good thing. I would recommend most people, even if you think you got this, I would kind of watch this a little bit. I think this is something that'll save you some time. So what does that mean then? What do we have to do if we want to find an equation line? We just need a slope and a point, right? Well, the calculus part, the hard part is the slope. So what would we have to do to this function to pre-write it? Most of what we do in calculus is rewriting stuff in order to be able to do calculus. It's very seldom, I mean really, the calculus most of the time is pretty short, intense bursts of math, and then everything else is just a bunch of algebra, right? So what are we going to have to do to this to get it ready to differentiate?
Plug in x to get the y coordinate.
Okay, so one thing we're going to have to do is we want to get the other part of the point of tangency. So x is 1. If I plug 1 in, what do I get back for y? 1/3. Okay, so I get, there's my point of tangency. Okay, but to get the slope, I'm going to have to differentiate, right? But I have to rewrite or pre-write prior to differentiating. What does the word differentiating mean? Taking a derivative, right? To differentiate, that's the verb for taking a derivative. Yes, sir?
Write it as a sum.
Okay, yeah, good. We've got to write this as a sum of two terms, each of which has a power of x. So we're just going to split the fraction, right? So this is going to look like y equals x cubed over 6x plus 1 over 6x, right? And then how can I simplify that? What does this become? Okay, good. So I'm going to get, if I divide like bases, I just subtract exponents, right? So I have x to the 3 minus 1 on the top. So x squared over 6 plus 1/6 x to the negative 1, right? Okay, now I can differentiate, right? So what's y prime going to be? First term,
2x.
good, I'm going to bring the 2 down in front. I'm going to get 2 times x to the 1, but I already have this. Dividing by 6 is the very same thing as multiplying by 1/6, right? So I get 1/3. Right, so we're just going to combine that 2 with the 6 on the bottom with the 1/6, and I get 2/6. So I get a result of 1/3 x. And then how about here? What's the power rule tell me here? I've got to bring the exponent down. Okay, so I get minus 1/6. Negative 1 times the 1/6 that's already there is negative 1/6. And what power do I end up with? Negative 2, because I'm going to subtract 1 from this. Okay, so then that's just equal to 1/3 x minus 1 over 6x squared, right? If I write this in terms of a positive exponent. Okay, so that's my derivative function. If I want to come back and get the slope of the tangent line then, and that's what I need, right? This is going to be the stuff that I need to do algebra 1 and find the equation of the line, right? How do I find the slope of the tangent line at this point? Yeah, I'm just going to evaluate the derivative at x equals 1, right? So So then whoops, equals y prime at x equals 1. So that's going to be what? If I plug in 1 there, I'm going to get 1/3 minus 1/6. What's that? 1/6. Good. And then from there on out, that's no big deal. It's going to calculate the equation of the line. Right? That gives us the ingredients. Okay? All right. Other types of questions on there that you need a hint on? Same kind of thing, right? If we want to know where a tangent is parallel to the x-axis, that's kind of code for what?
Slope of 0.
Slope of 0, right. Horizontal line would have a slope of 0. So we'd be setting the derivative equal to 0, right? And just solving to find the x values where that happens. Okay? Okay. More of the same. Oh, you know what? That's not a very fair problem. Did you guys get one like this?
Yeah, I have that exact.
Did you get the answer?
I was just working on it.
How are you going to do that one? That's what I want to know. I gotta make that one worth 0 because you guys can't do that yet. That's a problem that you can't do till today. Yeah, because you can't see the difference here. I mean, this is worth just taking a quick peek at, though. The reason we can't do that is because I can't split that into 2 fractions, right? You see the difference? Because the bottom is written as a sum, and that's different. If the bottom is a sum, we can't split it. We can only split it if we have a common denominator that has a single term, right? So that one, I'm afraid, I will just go in there and make that one worth 0. Yeah, so you can just skip that one. There was that number 5 on that second one. Yeah. Yeah, that's fine. You'll see that on the next assignment anyway. Okay. Well, that was good. We looked at that. Huh. I'll do it right now. Well, actually, no, this is the wrong thing. Can't do it on here. Cancel. Oh, can I even do that? Tell you what, you'll know how to do it after today, so you still have to do it, but it'll be for the next. I'll just push the due date off a little bit. You can do it as practice for the next one, next assignment. Okay, so what about let's go to this one, 2.2 practice 3. Not that there's anything super hard on this, but it uses a different standard form. We use a different derivative, right? Derivative rule. So let's just see. Wasn't this like only 3 or 4 questions though? Number 3? Sure. Oh, yeah. Okay, yeah. This is, okay. This gets us ready for something we're going to do later. And it's a really important connection to make. We haven't talked a lot about this yet. So if we write the area of an equilateral triangle as a function of side length, and it doesn't really matter which one, I mean, they're all going to be very similar, right? It doesn't matter what, I think most of them are geometric. Maybe not all the ones you could have gotten on this, but I think most of them are geometric. Write the area of an equilateral triangle as a function of the side length s, okay? So, oh man, this doesn't work. There, I can do that. Let me just grab a picture of this. We'll just talk about this a little bit. Okay, so what is that real quick? What is area of an equilateral triangle? Does anybody know that formula? What is the area of an equilateral triangle as a function of side length? There is a, I can't remember what it is. There is a way to write area of an equilateral triangle as a function of side length. We can just derive it real quick. If you have, I think it's like, what would it be? It's gonna be probably square root of 3 over 4 times s squared, I think. Is that right? Yeah. So how do we get that? You know, well, you know what? You guys can turn it. I'm not gonna. You guys do that. That's just math. You guys can do that stuff. So we'll just say that we get that formula though. Okay. So and you can do it just by dropping down an altitude, and right. I mean, you can figure it out. Area as a function of side length. What are we calling side lengths? Tell us. Side length s. So a of s equals square root of 3 over 4 s squared. Okay? When they want us to find the instantaneous rate of change of area with respect to side s, does it make sense to you guys that that means a derivative? Right? Okay, that's something I want you to, we got to make that jump. We've talked about a derivative. At this point, we've really only focused on a derivative as being the slope of the tangent line. Okay? But let's make a connection here. If I were to do a graph here, and this is really big, everybody close your stuff down and look at this, because this is important. I want you to, this is one of the biggest skills, one of the most important skills to have in math, is to be able to cultivate the ability to think about a function in terms of a graph space, right? We usually graph things in the regular Cartesian plane, the xy plane, but not in physics, right? Or in, you know, we can look at functions that mean something, like this, represent something geometrically. And really all we're doing when we're graphing something in a Cartesian space is we're graphing an output value versus an input value, right? Y equals f of x. We all know that, right? So when we graph something on the xy plane, x is the input variable, right? And y is represented by some function, right? If we're going to graph some function here, y equals f of x, that's the output, right? So we always do that. So what if we're going to graph area of an equilateral triangle as a function of side length s? What would the two-dimensional space look like where we would represent that graph? What's going to go on the horizontal axis? S, the side length, right? So for a given value of side length, this formula is going to output a value for area, right? So this is going to be A of S. Okay, and what does that look like? This is just some constant times s squared. So that would be like y equals some constant times x squared. Well, what does that look like? You guys know what that looks like. That's just going to be a parabola with a vertex where? No. At where? 0, 0, right? Okay, and how do we know that? I mean, this is, you know, I'm not going to do a complete review of this. I don't really need to, but just think of it this way, right? If we're gonna write a quadratic function in vertex form, just remember what that looks like, right? That's just going to look like a times the quantity x minus h squared plus k, right? All we've done is transform. H is the horizontal translation for any function, right? K is the vertical translation, right? A is just the stretch value, right? How much we're going to vertically stretch or compress it. If it's negative, we're reflecting over the x-axis. Remember that stuff? Right? So we can take any parent function, and by subtracting something from x, which we're always going to label h, inside the function, that's translating it left and right. By adding or subtracting some constant, that's the vertical offset, right? And so what are those values here? Well, 0. We haven't subtracted anything from s inside the function. It's not the quantity s plus or minus something squared, so it must be 0. And there's nothing added at the end. So we know that this thing hasn't been offset, and so its vertex has to be at the origin, right? Is that basically ringing a bell?
Yes.
Okay. Okay, so then our function just looks like this, right? Okay, so what would a slope represent on this graph? Think about it that way. So if we take a point on this graph, like let's just take that point right there, which corresponds to a certain side length and a certain area, right? Well, what is the slope of that tangent line telling us? It's actually something really profound, and we're going to talk more about this in much greater detail later in this chapter when we talk about something called related rates. But I want you to start to think about this concept right now, okay? If I were to describe the slope of that line, a line in XY space up here, like if this tangent line, we know that the slope of that is always just going to be delta y over delta x, right? Change in y over change in x. Everybody agree? Okay. So this is going to be delta a over delta s, right? So if I took any line in this space and I want to define a slope with 2 points on that line, the slope of, like for example, if we made a secant line, just for a second, let's make a secant line. So there's a point and there's a point. If I connect those, get an average rate of change, but lots of concepts come together here, right? Average rate of change is just a rate of change between two values of S and A, right? Right, so that's an average rate of change from here to here, okay? We would calculate that as change in A over change in S. Okay, how much did the area change compared to how much the side length changed, right? Well, what if we want an instantaneous rate of change? We could just back up these 2 points so they converge at a single point, right? And then the slope would be a derivative, right? Same way it was for us with f of x and x. It's going to work just as well with a of s and s, right? So then what is this going to become? Well, the slope of this line is still going to be the change in a over the change in s, but now we're going to write it as a derivative, right? So we could either write that as a prime of s or as dA ds. Just different notations. This notation, though, is pretty meaningful, isn't it? Because, remember, d is a baby delta, right? It's just like saying that's going to be a microscopic change in A over a microscopic change in S, right? So this derivative now, if you think about this, what have we done? We've said, okay, we're just going to graph area versus side length. We can see that because this quantity is area and this quantity is side length, a slope of a line has to be written in terms of change in area over change in side length, right? So what is that really telling us then? The derivative is telling us the rate of change of area with respect to side length. If the tangent line has a slope right here, let's just say theoretically that the value of the tangent is 5. That has some meaning. If we attach units to this, like let's say we're going to use meters and square meters, whatever, right? Then that's telling us that for this particular value of side length, the area is changing at a rate of 5 square meters per meter of side length, right? That's telling us how fast, as we increase side length, is the area increasing, right? Instantaneously. It's like saying in your car, if I'm driving down the road and my speedometer says 50 miles per hour, you get a sense of what that means. It doesn't mean that I'm necessarily going to go 50 miles in the next hour. It's just saying that if I maintained that speed right there, I would go 50 miles in the next hour, right? If I maintained this rate of change right here, I would increase the area by 5 square meters as I increase the side length by 1 meter, right? Now, it's not going to continue at that pace. It's going to continue to change along the function, but instantaneously, that gives you a sense of how fast is the area changing as I extend the length of a side, right? You get that? Mm-hmm. So that gives us a whole different appreciation of what a derivative represents. Yeah, it represents the slope of a tangent line. And we just showed that if we, depending on what space we're graphing something in, we can see that that means, you know, different quantities than just x and y. But without even graphing it now, I want you to just kind of see that anytime we talk about a derivative, it's always a rate of change. Always a rate of change, right? If we're talking about taking a derivative of, let's say we're blowing up a balloon. And the balloon, we're measuring the radius in centimeters, and so therefore the volume in cubic centimeters. Volume is a function of radius, isn't it? Right? If I take the derivative of volume with respect to radius, what's that telling me? rate of change of volume with respect to radius. So it's telling me for a given radius, how fast is the volume increasing, right? As I increase the radius of this balloon, let's say I increase the radius at a constant rate. Initially, the volume's not increasing that fast, but as the volume gets really big, if I continue to increase that radius at a continuous rate, well, the volume starts to increase at huge amounts, right? It takes a lot of extra volume to go from this balloon to that balloon, right? It doesn't take very much to go from this balloon to that balloon. There's not that much additional volume, right? The derivative is telling us how fast are those rates, how fast is one rate changing with respect to the other, right? You're not gonna have, I'm sure that isn't just crystal clear, but it'll give you at least a little bit of a, I mean, the idea, the reason I gave you this problem is just because it gives you a chance to kind of mull that over a little bit before we jump into it with both feet here later on in the chapter, okay? All right. Okay, so maybe that helps, I don't know. Does that help? Yeah, good. Okay.
Did you get the side?
How do you get what now?
The square root of 3 over 4 squared.
Okay, so how do you get that? You would just, here, we'll look at it real quick. So you would just go like this. Right, you would just say, here's how I would do it. So if those are all S, right, I could drop down in altitudes, then that's gonna be 1/2 S. Everybody agree? So if that's S and that's 1/2 S, then this is just a, this is gonna be a, that's a 60-degree angle, right? They're all 60, so that's gonna be a 30, 60, 90 triangle. So remember the ratios in there, I mean, we could use sine stuff, but if that's 1/2 S, then this has to be the square root of 3 times the short leg. So this is gonna be square root of 3 over 2S is the altitude. Right, everybody agree? So now we have enough. We know that the area of a triangle is equal to 1/2 the base times the height. So that's gonna give us 1/2 times S times the height, which is square root of 3 over 2S. So we get square root of 3 over 4S squared. Okay? I never remember that, I just always draw pictures. I can figure it out, you know, it's, I don't wanna waste those brain cells. Okay, so what now?
Oh, it's gonna be- It's, mine was the perimeter of the square.
Perimeter of a square, okay.
No, I already got all of it, it was pretty easy. but-
Yeah, so then the rest of it, well, find the instantaneous rate of change of A with respect to S. Well, you're just taking a derivative, right? So that, remember, that, all that means is dA ds, or A prime of S. So you would just be differentiating whatever you know, whatever you had for your problem, right? Evaluate the rate of change when S equals 1 or 6. We're just plugging in values, right?
You're plugging into the 3/4.
No, into the derivative. See, part B of this, part B wants you to actually take this, so here's an area function, right? Part B wants you to find, take the derivative, but it just uses the power rule, right? See what I'm saying? So when you take a derivative there, what this problem is really showing you is that you have the tools now to take a derivative of this function, but what's it mean? When you take that derivative, it's a rate of change of area with respect to side length, right? So you could say then, if we want to evaluate the rate of change of area at S equals 1 compared to S equals 6, you know, we're going to see that the rate of change is, you know, we're going to get different rates of change. The area is changing with respect to side length. As I extend the side length a little bit, the area is changing a lot more when the side length is bigger than when it's smaller. Okay?
So part B would be like 3/16 S.
Square root of, it would be, in this case it would be square root of 3 over 2S.
The easier one on me.
Because I bring the 2 down. See what I'm saying? When I differentiate, I would just multiply square root of 3 over 4 times 2. And then just subtract 1 from the exponent. Okay? Yes, sir.
So assuming those 3 points you have are A, B, and C, and B B lies perfectly between A and C, then the tangent line of A and C is exactly the same as the slope of the point B.
Yeah, and that's,
Okay.
okay, so that's something, you're right, and that's, we're gonna call that the mean value theorem for derivatives, and we'll talk about that soon too. But that, we haven't gotten there yet, but that is true, yeah.
That makes a lot of sense.
That's a pretty good observation. Okay, so here's our one item of business we're gonna take care of today. Okay, so now, everybody, I'm gonna cut into your work time here, so click those things closed all the way, please.
Oh, all the way, okay.
Okay, so what we wanna do something really important. This is gonna be very helpful. We wanna come up with a product rule. We want to come up with a rule so we could take, if we have two functions, f of x and g of x, our goal is by the end of the day, we want to come up with a way that we could find out, we could calculate what the derivative of a product of two functions is. You know, like right now, if we wanted to do something like this, like if we wanted to do, let's say, the derivative, if we had y equals the quantity x cubed minus 3x squared plus 4 times the square root of x minus x plus 3. Our only way we could do that would be to expand this whole thing out and differentiate term by term, right? What if we wanted to do something like this, like y equals, say if we want to calculate y prime, I'm saying. What if we had y equals x times sine x? We have no way to do that problem now, right? We have no way to do that one because it's a product of two functions that we can't write as a sum of terms, power rule terms. So we're stuck. So by the end of the day, we want to be able to A, do this problem without having to expand it out, and B, do that problem, which we can't do at all right now, okay? So you understand the need for this, the great need for this derivative rule, okay? Okay, so then let's do this. So we're going to start from the beginning, right? Start general and get specific. So let's just start with our basic derivative rule, right? So we know that f prime of x just equals the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0. So let's get specific then. Okay, so what are we going to do next here? Okay, so let's see. Richard, how's that going to work? If I do f prime of the derivative up here then, whoops, I don't do f prime. So we're going to take this function up here. We want to take this derivative. I'm just going to call it y prime. What is that in terms of our general rule then? So in this case, we're taking a derivative of f of x times g of x. So what's that going to, instead of just f of x, so what are we going to get here? Question?
Yeah. How come we didn't reduce the f of x minus f of c over x minus c?
You feel like that one was kind of left out. I feel bad for it.
Why? Because you don't have the delta x.
I think it's easier.
In some cases, it's easier. In this case, it would be a little bit harder. Yeah, and it's in some cases it is a little bit easier. In this case, it would be a little tougher to do. Yeah, in this one, we want to be able to let delta x's go to 0. And how do I know that? I don't know. Just because that's the way we do it. I don't care. I can looking ahead, I can see why the other one would be a little bit tough. But that's not an issue. How often are we ever going to use this limit definition from this point forward? Almost never. Like today, whenever we're going to try to develop a new derivative rule, we'll use it. But then we're going to use the derivative rule. The derivative rules are what agreed. I bet you like this assignment a lot more than the 2.1 assignments where you had to do those big long limits, right? I mean, it's way easier to use the derivative rules. So we never really do this, except when we're just trying to prove a new rule, right? So what's this going to look like then, Richard? If I've got my function up here, I've got two of them put together, instead of just f of x plus delta x, what am I going to get? Well, no, it's not f of g, it's f of x times g of x. So I'm just gonna have to have, when I evaluate this whole thing at x plus delta x, and this, I mean, did everybody see that this is what I'd get? I'm just gonna get f of x plus delta x times g of x plus delta x, good. Minus f of x times g of x, okay? And that's all gonna be over delta x as delta x goes to 0. Now I wanted to show you this. This is one I like to do just because it's weird. We almost never do something like this. We almost always manipulate an algebraic expression by multiplying by 1 in the form of something divided by itself. We've done that a lot this year already, right? We almost never add 0, but this is one where you add 0. And this is kind of a mystery step. I mean, why would we do it the way we do it? It's just, you'll see how it works. And then maybe when you reverse engineer something, a lot of times you can see the motivation for that step. So that's what I'll challenge you to tell me is why was this step, why would you maybe think about a step like this in the future, okay? Okay, here's the step I'm gonna do. In the middle here, between these two terms, I'm gonna add 0. I'm going to add 0 in this form. I'm going to subtract f of x, I got to think about this. X plus, yes, this will work. F of x plus delta x times g of x, and then I'm going to add the same thing, so they add to 0. And then at the end, I've got my minus f of x, g of x. Okay, everybody agree that adds to 0? Okay? Because it adds to 0, 0 is the identity number for addition, I haven't changed the expression. It still has the same value as before when I add 0 to it, right? Okay, why am I doing that? No idea. Okay, no idea. It's a mystery. Okay, let's regroup this a little bit. I'm going to group it into two parts. That part and this part, okay? First part, can I factor something out? F of x plus delta x, yes I can. Okay, so then we're going to get the limit of f of x plus delta x times what's left over. G of x plus delta x. Aha, okay. Okay, plus over here, use a different color bracket, just so maybe that'll be useful later. I can't think that far ahead. Maybe it will. So what can I factor out over here? G of x. Do we agree? Okay. Okay, so second word, yes. Yes. Okay. 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 This is right. This is right. So I factor out a g of x, and then I'm left behind with minus f of x. Good. Okay. Yeah, this is good. This is good. This is gonna work.
Yeah.
Okay. So
3 different brackets.
and then over delta x, right? Okay. So now let's take this first group. Let's take this first group together. And we're gonna break this up, so I'm gonna rewrite this very subtly, and you tell me if you see why this makes sense. F of x plus delta x times the quotient g of x plus delta x minus g of x over delta x, okay, plus Okay, we're seeing some, lights are clicking on here, I can hear them, hear those switches. Plus, I'm gonna write this g of x times the quantity okay, right? And let's even break this up into two separate limits. Not that that's that big a deal, but I'm just going to add another limit right there as delta x goes to 0. I can split it into separate limits, right? Okay? Okay, what does this represent? What is the limit? I'll go one step further. Let's break it into 4 separate limits. No, we don't need to. We don't need to. I'm running out of time if I do. We don't need to. Okay, what does this limit represent? Think about this. As x goes to 0, everybody should recognize that. What is that? Okay, that's a derivative, isn't it? Right? That's g prime of x, isn't it? Right? Everybody see that? That's our standard form, but instead of an f of x, it's a g of x, right? Ooh, how cool is that? Okay.
And then you have the other one right there. Spooky.
And then we just do everything again to 2 separate ones.
Yeah, so that's just g prime of x, right? Plus, how about over here? I've got the limit of g of x, right? Times, what's that? F prime of x, right? That whole thing is just f prime of x. The limit of f of x plus delta x minus f of x over delta x, and delta x goes to 0. That's just f prime of x.
Is that the limit of g of x?
Right, so it's the limit of, and now we can take our limit. As delta x goes to 0, well, that's what we get over here, isn't it? Right? Because that's what this means. The limit, g of x, there's no delta x in it. So in the limit, it doesn't change at all, right? This becomes f prime of x. Well, what about over here on the other side? The limit of this, as delta x goes to 0, became g prime. Well, what happens here? What's the limit of x plus delta x as delta x goes to 0? F of x. How about that? So we got a rule. Okay, so our rule is, look at this. We're done. So this is equal to f of x times g prime of x plus g of x times f prime of x. There's our product rule. Okay, if I'm taking the product of two functions, it's just going to be one function times the derivative of the other plus vice versa, right? In no particular order, right? Because we're adding the terms, it's commutative. It doesn't really matter which one you differentiate first, right? So let's deal with our problem here. Oh, that's all we need. That's all we need. So if we want to calculate y prime here for this problem that we couldn't previously do, we got it. One function is x and one function is sine x, right? So what are we going to get? We're going to get x times the derivative with respect to x of sine x plus sine x times the derivative with respect to x of x, right? What's the derivative of sine x? Cosine. So the answer is going to be x cosine x. What's the derivative of x? 1. Done. Right? Easy. How about that? Boy, that's a lot of math we did there in about 20 minutes. Right?
20 minutes.
Okay.
Only 20 minutes. It only took us 20 minutes. That's an easy problem right there.
That means my 10 question